Excellent. So thank you for joining this webinar, which is going to be a very interesting webinar because whilst the title is Decarbonisation in the Transport Industry, you can see from the subtitle is what we're really looking at today is balancing the environmental benefit that we all know about, and we'll drill into it a little bit in a few moments, but against very importantly, the bottom line economics. How can you do that? And how can you potentially look at the potential effect of both the economics and the benefit prior to employing any of the devices in your organization? And that's far more important. And we find a lot of people at conferences and exhibitions we go to, a lot of people come and talk to us about this exact topic. They know they want to decarbonize. They know it's important, but they also know from their financial directives that there are economics to be looking at. And they're trying to say, how do we know what we can do? And will it give us the benefit we actually want? And can we afford that benefit? And has it made the right difference? Can we measure that benefit? And that's precisely what we're going to be looking at today. So without further ado, let's just introduce everybody. There's myself, just kicking off, Michael Boyle. I'm head of sales here for Anico Data Engineering, and I'm really looking forward to the fact that we're joined by MH Tech, a really brilliant company in this field around this analysis that you're going to be learning about. And it's Robert Helm that'll be talking today. He's a CGO at MH Tech. And also back at Anico, our very own CEO, Colm Hayden, will be really then breaking into the data aspects of what Robert is going to be unearthing. So just as we move into the agenda and the actual topics that we're going to be talking about, just a little bit of housekeeping, as we always do, is this is being recorded. The recording will, of course, be sent out to everyone. For those who have registered, there's a wealth of people who registered today over the last couple of weeks and have already been notifying us that they couldn't join today, and that's not a problem because we're recording it and we'll send it out and we'll be in touch and we can chat about the topics that you'll be learning around. For those of you today, it is being recorded. You're all on mute. If you have a question, pop it into the chat, and then we can take that question. We can either take it whilst we're running along, or we can take it at the end where we will have a session for the Q&A, and we can go through some of the questions then. If you would be so kind, if you could turn you're all muted, but if you could also turn your videos off, that just helps everybody focus on the PowerPoint itself and the topics that we'll be talking about. That's fantastic. Appreciate that. So let's look at the agenda. I'll be just very sort of setting the scene. I'm looking at, well, what is this topic about balancing environmental benefit against business economics? That's what I'll be talking about. Then we're going to hand over to Robert, who's really going to break into the detail about modeling, fleet modeling in this particular case. And in this case, it's for decarbonisation, but it doesn't have to be. And that's why it's so interesting to have MH Tech talking today, is because they can do strategies all around energy analysis and how it's beneficial for your business. But we're specifically focusing on fleet as a good example and decarbonisation because it's extremely important in the world that we're in today. Then we'll get over to Colm, as I say, Colm, our CEO, and he's going to really then break into the data and why that's absolutely key to everything. It's the starting point and the end point. And that's what we'll really hopefully get over to everyone today. Very, very briefly, as we always do, we're not here to labor a load of slides at you about Anico and all of this, but let's just cover the most important piece, that the keywords here. Anico, we're data engineers, but the most important thing is we are collaborative friendly. That's why we have companies like MH Tech and Ether and all these companies that we've had recently on. We're all about collaborating, and the reason we do that is so that we can offer a better, full, complete service to our partners and our customers. rather than just offering one piece of the jigsaw. It's important to link up across all of these experts to really be able to provide that full solution. And what we focus on and what we are experts in is providing, building and operating sustainable and ethical data platforms and the analysis and reporting thereon. What we do and our mission that we stand to every day is delivering environmental and societal benefit through that timely access to quality data. These are very important words. It's not just about data, it's quality and timely access. And this is most important. That's what we do. Of course, we'd love to talk to you more about what we do and how we can do it for your business, but that's for another day. What we want to do is crack on into this subject. So, balancing vital environmental goals with the economic viability. It is clear to everyone when we talk about this subject that we must meet our Paris Agreement. We are focused toward delivering that Paris Agreement. So there are climate goals. But when we look into this, what we have seen, and the reason we pick this as a key topic all the time, is that transportation itself accounts for 23% of the global greenhouse gas emissions. So if you're going to focus on something, this is always a good one to focus on. So when we're talking about shifting domestic to public, when we're talking about fossil fuel to other forms of energy, this is what always counts towards achieving those climate goals, and we can reduce the emissions by doing so. That's not what today's about. It's just a very obvious point that it brings everyone into this discussion. What we know as well is that, and it can be argued, that it brings both economic and social benefits. Because if you bring and improve the environment, we know we will get both economic and social benefits. The economic is that it can actually produce jobs in these new greenfield areas. So that's why it can be economic. But social benefits are also extremely obvious. The energy independence is also far more important when you start drilling down, because it's starting to remove the reliance on fossil fuels. It's not saying completely remove it, it's becoming independent from it by being able to use these other fuels. And hydrogen, of course, is one that we're starting to get a lot of traction. But electric, of course, is where we're moving to, but there's still a reliance on fossil fuels to produce the electric. So that's where we've got to start looking, and that's why Robert's team, MH Tech, is starting to look at the energy, specifically on that energy. But of course, also what it can do is reduce long-term costs. But again, that is very important. Even when we're looking at wind energy and things like this, there are a great deal of costs. Although they are environmentally friendly, there are very high costs involved in actually the maintenance of such items. So there's a lot of factors to bring to bear. It's not just a case of we need to decarbonize, therefore let's do, because it has to be afforded. So let's come to that exact point. What are those challenges? The high capital investment is what really causes most people to stand back and say, can we really do this? Is it the right thing to do? Is the market and the tech ready? Are we making the right decisions rather than just the first thing that is coming to us? So again, can we look at those tech, and can we look into the market numbers and extract data from it to make decisions? These are the questions, because these are what will reduce those challenges towards all heading towards that Paris Agreement. Can we finance it? How can we finance it? Are there ways of funding these types of process and these types of technical aspects that can mitigate the reasons for not going down that path? And then there's always the unknown. We don't know what we don't know. As anyone who studied environmental analysis would know, is that when you change one feature in the environment, you've what you don't know is what can backfill that gap, that empty space. And we don't always know what can happen there. It's a little bit like when they used to dredge bay areas, Cardiff Bay and places like this. When you dredge, you don't actually know what is actually going to happen. But if you can do predictive analysis to know what's going to happen, then before you do the dredging, you will actually know what type of shift movements you will get. You will know whether certain land would move from upriver, for example, which was the case in Cardiff Bay. So we don't always know just by applying there and then analysis. It's the predictive analysis that can bring us and bear us to the truth. So let's look into that. What is that? How can we bridge up that gap between the two? Well, what we can start doing and what we'll break into today is, can we look at scenario analysis? Can we look at, if we were, say, for example, TransLink, one of our customers, if they are shifting to electric, and if they move all of the fleet to electric, how do we ensure, for example, that everyone will get out of their car and get onto the bus? Because there's no point in providing all of the buses if everyone stays in the cars. So those scenarios need to be analysed and passed through. So there needs to be methods of getting people out of the cars, not just providing the electric buses. In that respect, can you do a cost benefit modelling? Again, you can't just buy 50 buses if people aren't using them and there isn't some method of financing that route going forward. And that then starts to push through to demand forecasting. How do we know how many people will be using a certain train at a certain time of day? Can we break up those times of day? Can we work with different industries to ensure that people are starting and finishing at different times so that demand doesn't peak at the wrong times? So these are all the pieces. And through all of these is risk. And risk is what we're trying to mitigate at all points. And in terms of trying to mitigate it, we're looking at technology. We're looking at supply chain and how we can look across that supply chain. Compliance is always there as nearly the elephant in the room, because it's a piece that you cannot ignore. It's, if we look at CSRD and ESG, these are elements that are coming at us, and we have to actually accept these and move forward with compliance. And in doing so, we can actually reduce the risk. In doing all of these pieces, if we have the data in the first place, and the data is something that we can trust, then we can do that analysis, both the predictive and the real-time analysis following on from that. So trusting the data is one thing, but also understanding that the data comes from so many different sources, and understanding those different sources is what Anico specializes in. It isn't just the platform to house it upon, but it's actually ensuring that you know where the data is coming from and that you can trust it and it is viable. At that stage, you can then actually do dynamic monitoring or real-time monitoring. And once you can do the real-time monitoring, you can actually then feed in data into decisions that are being made, into policies that are being made, because there is real evidence. And those policies now can be real and justified because the data is trusted, it's real time, and therefore it can be acted upon. And as a result of that, finally, you can then optimize the investments. You can modify and adjust because everything is in real time rather than extremely post-dated data. So that's really the summary of what we're trying to achieve today. And that's where I want to now hand over to Robert to drill into what is this predictive analysis and how can we start to look at this type of data. So Robert, if you could unmute yourself, if that's okay, and if you could put up your slides, and I'll hand over to you.
Sure, thanks, Mike. I'll start sharing now, so hopefully people can see that.
We can.
Great. Okay, fantastic. Yeah, thanks to everyone for joining, and thanks to Mike for that run-in. We are MH Tech. Myself and my colleague Ole Harold are on the call just now, and we're a Norway-UK business focused on decarbonisation of complex energy systems. So what we're going to cover today is some of the points that Mike touched upon there, in particular the de-risking and ensuring cost benefit of the transition to decarbonisation, but with specific focus on the modelling elements. So how do we use modelling in that context? And we're linking back to data and data sources there. So leveraging the data to make the right decisions fundamentally. So we'll run through a few slides here. We've got a quick introduction to our business. We'll look at fleet operations or transport operations. What are they, and what is modelling fundamentally? And then a use case to describe and demonstrate how we've used fleet modelling in a decarbonisation case. And then we talk about what's the next steps in modelling. So how do you move from, say, a static model, which could be used for decision making, into a dynamic model environment, and a quick wrap up. So as an introduction to our business, we are a business founded in Norway and set up and live in the UK. So Norway, UK business, founded on a full-time basis in Norway in 2020 and in the UK 2023. We have originated from a focus on energy and energy consumption, specifically with a view to transitioning to green and sustainable activities. So our focus as an organization very much on the sustainable use of resources in the transition. And resources, we mean everything from the minerals and the metals through to the money. Future focused, so a big part of what we do is ensuring that the solutions that we are recommending to our clients are no regret, they're future fit. And a big part for us, kind of core to our philosophy, is delivering the best cost benefit solutions to our customers. Decarbonisation specifically can be a challenging space to overcome some of the hurdles initially, the capex hurdles, for instance. And what we look for is deriving the technology scenarios and rollout that address and even become cost beneficial in decarbonisation. We're a technology-led business. We work with data analytics in the first instance and use our own in-house developed software to understand the energy landscape of a energy system. Broadly, how we work is we'll approach from the analytics and the modelling end. We'll survey what information we have. We build a model of the system we're looking at. And by system, in this instance, we're talking about a fleet operation. We can, using our modeling and analytics capability, we can model either an existing operation or indeed, depending on data availability, a future fleet operation, which is the case study I'll touch on later. We use our own in-house energy simulation software. So this was developed, in fact, for Norway's nearshore maritime industry and then transitioned through a relationship with Siemens in Norway into the onshore and road environment. So this is really the core of what we do in many ways. We understand the energy and predict the energy requirement of future journeys. So before a trip has been taken, we can predict the energy requirement on an accurate basis, looking at the characteristics of that journey. And I'll touch on that a little bit later as well. We are from an engineering background, so we pride ourselves on that, and we apply an engineering mindset in everything that we do. So we're completely technology agnostic. We're not focused on one particular solution, but we'll cover many and all and screen appropriately. Ultimately, we're looking for right-sized infrastructure, and that's what I'll demonstrate today and how we use modelling to arrive at that future fit solution. So quickly into fleet operations and transport operations. So the way we view transport operations is in one of three categories. So either fixed route operations, and the examples there would be, say, refuse collection programs from council and local authorities, public transport systems, buses, and similar infrastructure, and some elements of long-haul freight and distribution freight that would come under fixed route operations. Fixed route obviously lends itself to modelling quite well. Slightly more complex and complicated is event-driven operations. So these would be anything from emergency response fleet through to maintenance activities. For example, for utility companies maintaining their electrical or water infrastructure, for instance, and last mile delivery. So an added level of complexity there for these fleets in modeling their operations. And then site-based operations, an area of kind of increasing focus and activity for us, certainly. But how do you model a construction project or an agricultural industrial complex or indeed a mining operation? So what is modeling? For us, it's considering either existing operations, so that might be an ongoing and live operation. It might be considering prospective operations. So maybe your organization is active in a tender process or in a merger and acquisition process, and you want to understand what it is that you're approaching. And also future operations. So perhaps you are looking at expansion of your own business, you have new depots to set up and run, or indeed you might have won a new contract and you want to understand how that operates. So our perspective covers all those angles. The purpose of the model, why might you model? What drives you to model an operation? Optimization is the obvious one, so testing and understanding optimization opportunity, ensuring optimized utilization of your assets, considering operational change, of course, and in that we include planning for future events, of which, of course, decarbonisation is an obvious one in the transport world, as Mike's touched upon. Certainly in the UK, transport is now the highest polluting sector after the reduction in carbon emissions from power generation over the last number of years. And then where do we take that? So we had a model and we've addressed these scenarios. Then where do we go? How do we improve that model so we can validate the model against real operations? If, for example, you're using a model on a future scenario, then you will want to validate that once you get up and running. And then, of course, the next step in improvement is moving to live data feeds and moving to a more dynamic model environment. The modeling process for us is using the data that we can find and get our hands on. So in ongoing fleet operations, that might be telematics or transport management system information or data feeds. For future operations, and indeed in the case study that we covered just now, it might be more along the lines of event information. So that's emergency event information or any record of activity that has become before that might inform your model. From there, moving into the transformation of that data into a useful model. So cleaning and validation, integrating the data in the model, and then understanding what you want to get and engineering the features there. In our instance, what we're looking for is mileage, modeling the mileage of the fleet at a vehicle and duty cycle level and aggregating that up to depot and operational level. And thereby being able to run that mileage model through our energy simulation software and really get to grips with the energy demand of that fleet. Understanding the energy demand can help you understand where to optimize. And of course, what your options are in terms of decarbonisation opportunity. We'll also embed a predictive analytics element to use what data we have as data sources, use that data, understand what the future may look like. So that's how we build our models in the fleet space. The benefits I will breeze through relatively quickly, but we can understand that, of course, modeling brings the ability to visualize before implementation. So are there pinch points in your operation? Are there areas from our perspective anyway, and in this particular use case, energy intensity areas that you want to address that give you a target areas to prioritize your decarbonisation effort, for instance. It allows you to focus on optimization, so you can reveal inefficiencies in the operation, of course, and you can test and demonstrate optimizations through the virtual environment without having to actually implement or before implementing. In the decarbonisation space, modelling allows you to quantify those optimizations in the CO2 savings that are possible. And of course, pinpointing those decarbonisation target areas. And then in general, it covers all of the above, test and verification. So critically being able to test any optimization, planned change before actually rolling it out. So our use case at a high level, we were looking at decarbonisation pathways for what we'll term a complex fleet operation. I've got more detail on the following slide as to what that was. Our methodology, you'll kind of maybe recognize this from earlier on, or the fundamental way in which we approach this challenge. It's a complex fleet application in this instance. We'll look to model the fleet operation using whatever data we can, and fundamentally to understand the mileage and the predicted, the trends in the data and the predicted trends in the data. From that, we're pulling out energy demand. And then using that data, then we're looking at the decarbonisation pathway for that fleet. So a little bit more information there, moving into the model use case summary. The fleet operation in this instance was in fact a road maintenance fleet across a local authority area in England. So road maintenance fleet has an element of emergency response. Some road defects have to be responded to in a window of 90 minutes or less. So you can see that's getting up towards a kind of blue light fleet type operational performance requirement. So very challenging for decarbonisation anyway. And the operating mode for this particular model was that this was a future operation. So a contract had been secured, but there was no operational or vehicle information ready or available at that point in time. No operations existed. So it was how then did we model the operation? The purpose behind establishing the model, of course, was to understand the energy consumption and help us design the decarbonisation pathway. So in terms of data input, what we had was events data or defects data over the road network. We had depot locations, we had vehicle count, which had been designed by the operator for future implementation. And we were able to understand the operating principles of that fleet broadly. We used that information then to build up a model of how that fleet would operate and how it would respond to the defects in the data that we'd received. Again, what we want from that data is understand the duty cycles of the individual vehicles. So all the way down to vehicle level and across all the different weight categories of that fleet. I mentioned this was a complex fleet. You can imagine a road maintenance fleet, everything from supervisor vans up through the tarmac tipper vehicles, 7.5 ton or so, and upwards up to winter fleet. So duty cycles of all vehicles modeled in the model. Understanding there from mileage, understanding energy demand, and then moving into looking at data trends. So how did these things change over the course of the contract critically? The output at the other end and the use of the model was to understand how different decarbonisation technologies would fit this particular operating model. Then we would also look at optimization opportunities. So for example, let's say looking at electric vehicles, is there anything you could do to the fleet operation in terms of optimizations or tweaks as to how you were responding to the defects and the contract requirements, but that would allow you to increase the penetration in the fleet and up the overall penetration of decarbonised technology in that fleet. And of course, it would help us size the infrastructure for the decarbonised scenario, thereby allowing us to do a fully costed payback analysis. And I touch on the next steps there, which we'll follow up in a later slide. So to give you some insight into the build-up of the model and the sorts of data that we were using there, and I keep going back to some of Mike's points in my mind, certainly around the data quality and understanding, using that data to mitigate the risks. And that's really what this exercise is all about, especially in this road maintenance operation. Performance under the contract or non-performance would bring penalties and non-performance penalties. And therefore, designing a decarbonisation pathway that continues to assure operational performance is absolutely critical. So we needed good quality data, we needed a good quality model, and we needed really reliable outcomes. And this is how we went about it. We firstly modeled the defects or laid out the defects in our model, so over space and time. And you can see this in particular area of, so that would be over a calendar year, for instance, and indeed daily, and then really begin to understand how this fleet would operate. From there, we were having a knowledge of where the defects or the events existed in this instance. And this would apply to any fleet, any events-based or events-driven type fleet, knowing where the events were, how they occurred, when they occurred, and how the operating principles of the fleet. We were then able to model each and every individual vehicle journey from a depot over the course of a day, month, year. And this would allow us to build up energy profiles, energy requirement. So really get down to an optimized energy requirement. We're not over designing, we're not under designing critically, but we're just getting our energy availability in whatever form that is, whether it's electrical charging, electrical power, whether it might be biomethane gas or any other decarbonized energy source. We're making sure we get it right sized. At the same time, we're looking at trends in the data, particularly this bottom graph there, where we ran the predictive analytics algorithms on the 3 years of working data that we had to understand, and of course is a relatively simplified output, but just to understand what the future trend was over the course of the contract for this particular client. So how, we have to deliver the same service at the start of the contract as we do at the end of the contract. And what does that look like? What will be the event count that we have to respond to, and ergo the energy consumption of that fleet, making sure we're future fit. And then just to summarize on the overall kind of findings of the study there. So as touched on previously, the modeling process is actually something we undertake to inform the overall decarbonisation process. But back to Mike's points and the kind of urgency and requirement around decarbonisation, but also the cost barriers, we're using modelling to ensure that we can deliver a best cost and most reliable and operationally assured outcome for our customer base. So it's part of the process. It's not the whole process. But in this process for this particular customer and generally how we deliver, so this required a fairly deep dive on available data. So what's driving the decarbonisation requirement? What are the contractor requirements? What are the company's corporate requirements, the contractor's corporate requirements? And what are the governmental requirements around decarbonisation of different vehicle classes as well? So what data do we have? What delivery data do we have? The events data, etc. And what are the gaps? A constraints analysis around, okay, if we know where the depots are, what constraints might we face if we're trying to change our fueling technology? So we're into grid capacities, for instance, and constraints around electric and gas grid, indeed, if we're going biomethane. We understand more about the technologies and the geographical readiness of those technologies. Some technologies are very geographically dependent. For example, hydrogen might fall into that bucket right now, given the transportation of that particular fuel is challenging. And then infrastructure. Are there any public infrastructure that can support our decarbonisation of our operation? So really understanding that constraint and understanding through technologies such as isochrone analysis just how far different technologies might take us. So this is particularly applicable in the case of EV, of course, with the relatively limited range for larger vehicles, certainly. How far will the range of the vehicles take us on an out and back basis from our depot? And this gives some form of operational assurance from a visual perspective. So what did we learn from this process, from the modelling, certainly? Clearly, we got the trends, we got the future trends plus the annual trends. So we knew when and where the stress would be on the already designed delivery model. We understood across the 4 or 5 depots that we were looking at, again, where the stresses were, where were the underutilized vehicles and crew, and where were the overutilized, so we could really start to balance that operation a bit better. And of course, we could look into the future and make sure we used all that data combined to get the right size of infrastructure, which allowed us then to think about which technology, of course, and screen down to our final technologies. In this case, it was biomethane electric vehicles and renewable diesel, or HVO. We've sized the infrastructure. We can understand the payback analysis on each of those infrastructures, and we can also do a detailed analysis of the fit of the different infrastructures. So this chart on the bottom right, that was our distribution of vehicle days across the fleet operation that would work for electric vehicles on a very conservative range basis for 7.5 ton trucks. This happened to be, and those vehicle days that were outside, so higher than say 80 or 90 miles in a day. How often did this happen? I mean, overall, we think less than 10 or 15% of the operation. And then we can deep dive into these areas, which do not fit the particular technology in question. Can we optimize those particular vehicle days and get more of those vehicle days into that decarbonized technology? So it's another application and use case for the model. So just quickly as to how we actually move on from that static model. So on that particular use case, we were in static modeling, so static data, and using that to understand how we might decarbonize. Of course, as this operation goes live, what we want to do is move to a dynamic model, and we can test optimizations. We can understand real-time CO2 and emissions and energy consumption from a live model. So how do we do that? We're effectively validating the static model against operational data. So how do the results match up? Are the operating patterns turning out to be as was modeled? So we're doing a match up there. And then that static model becomes the basis of building a dynamic model. So we begin to look at the potential live data streams. These might be the telematics or transport management systems referred to earlier. And then you have to start thinking about real-time data processing. And I think this is where Colm and Eneco come in. Really, the strength in what our partners here provide is that they begin to think about the architecture and the requirements and the tools behind real-time processing of data streams and how you're storing and handling that data and what the hierarchies are. And then, of course, implementing that dynamic model. So just to cover in summary, I think the points at the beginning that Mike mentioned, decarbonization in general and the ESG requirements on operators are an ever-present. What we find as a company involved in the decarbonization of energy systems in general and fleet operation and transport operations in particular is that there's always a cost challenge. There can be a CapEx challenge, capital expenditure challenge in the first instance, but often for fleet operators, there's also a scale challenge. So actually you generally need to use quite a lot of this decarbonized fuel to begin to achieve payback on your capital outlay. So it's how do you best overcome that both capital and the scale challenge around deployment of decarbonization? And our answer certainly is modeling helps. It helps optimize and it helps make sure you're wringing the cost and getting the economics as spot on as you can and testing the solutions before you go into it. So ultimately, that's our aim. On the left-hand side here, we're about understanding the accurate energy demand. We can look at operations before they commence. We want to understand the future, so we use all the tools at our disposal to predict future trends of the operation, and we'll always look at absolutely cost-optimized outcomes. In modeling, we've talked a lot about that, of course, and the benefits of modeling. And why you might move from static to dynamic. And then in particular for decarbonization, again, to touch on that, right-sized infrastructure is critical, understanding what you need throughout the life of your operation, or indeed how you approach that with a modular type mindset and design mindset, so that you're not deploying all the capital up front. Cost optimization is critical. And using the model to look at operational adjustments to improve the fit of decarbonized technology best you can. And of course, you have to think about which fleet scenarios you're actually setting out to model and which data you've got. So thanks very much for everyone's attention, and happy to take questions as we go, of course. But for now, I'll hand back over to Colm for some Eneco view.
Thank you very much, Robert. Yes, extremely interesting. And Robert focused there on the modelling that informs many of these decarbonisation initiatives. And what I want to do is to talk about when you're moving from that modelling into operationalised implementation of decarbonisation, and looking at how data is key, how trusted data is key, and use a couple of examples that I can highlight some of the challenges and the opportunities within that. So I'll cover first an overview of how we look at analysing transport data. I will look at a mixed fleet scenario, very much like the road maintenance that Robert described. This happened to be for Northern Ireland Water. They had their maintenance, both light goods, vehicles, vans, small vans, 4x4s, as well as big tankers, trucks and trailers. I'll then take a look at decarbonisation of public transport and some lessons learned. Let me click there. And firstly, I want to start when Robert described how transport is now the biggest contributor to greenhouse gas emissions in the UK after the energy sector became more optimised. And within that transport sector, this table on the left shows the transport emissions across UK domestic, broken down by cars and taxis, heavy goods vehicles, vans, shipping, buses. And what you want to do in an overall system is to apply the avoid, shift, improve framework. So avoiding the use of travel and transport where possible. Shifting to more efficient modes of transport. So if we can shift people from their personal cars into buses, for example, in a chart, you can see there will be an advantage. And then improving the efficiency of vehicles, of public transport, and of the fuel use and the route within those. So how we look across the transport analysis, transport data analysis, is we first look at what happened. And Robert began by describing historical data, 3 years of data there where they could run some modeling. We also look back at historical data, but often to inform on how your targets within organizations are improving, month to month, week to week, quarter to quarter, year to year. And so very commonly that describes in a descriptive way the red, amber, green, rag reporting of targets. Then you deep dive into diagnostics. Why did something happen? So once you have described the journeys that were made and who made them, and you look at the emissions that resulted, then you might want to diagnose why those journeys were made. Then you move into predictive. So in predictive, in these, very often the need is about the capacity, the changing consumer habits in last mile delivery, or the passenger behavior, or the freight transport behavior. And so you're looking and predicting the capacity and the need of that system, and seeing if you have enough assets, right-sized, as Robert describes it, to meet that demand. To then moving into a prescriptive view, making recommendations. And this is truly where the promise of machine learning and AI can deliver the greatest benefit. But in order to make recommendations, you need to have trusted data. And that's where Anico steps in. We help organizations trust their data, centralize it, and make decisions based on it. So if I take an example of decarbonising a mixed fleet, Northern Ireland Water had 700 vehicles, and they want to inform their decarbonisation strategy by reporting across those. And the way they want to look at the economic impact balanced with that carbon reduction is to look at where the most costly vehicles could be replaced first. But when you're looking at a whole system view within a complex organization like Northern Ireland Water, there are many different stakeholders: fleet managers, finance, human resources, the drivers, heads of department, directors of operations, asset managers, and fuel managers and their suppliers. And so you need to understand the needs of each of these stakeholders, because they fall into the overall benefit and practicality of delivering the optimization solution. And some of the challenges when you come to do this is that you're extracting and aggregating information from many third-party sources, from fuel data to vehicle tracking. And there's good internal understanding within this business of their HR data, of their drivers, of their operations. And when they're third-party systems performing the vehicle tracking, they're very specialized purpose. So when you start to aggregate that raw data together, collate it from many sources, the least understood data comes from those third parties. And one thing you need to start off with is to come up with a common data model and understand that third-party supplier definitions can be different. And what is a journey in one system may not necessarily be a journey in another. So, for example, we were looking at range analysis to see which journeys were candidates for electric vehicle replacement. But some journeys were very short, and that was because a vehicle was being moved around the depot, around the yard, because it was in the way, and those needed to be filtered out. So having a clear definition was important. And while there's real-time telemetry, telematics, tracking these vehicles and collecting an increasing amount of data, when you look at a whole system view, those aggregation cycles are rarely real time when you collate everything together. So you need to understand how fresh and timely information is and ensure that you're considering that when bringing it together. And so we had a set of requirements, and I'm not going to go into all of these, but the fleet requirements were significant from an operational, contractual, and financial perspective. And first of all, looking at the asset register, the fleet number, registration date, purchase price, the count of vehicles per function, the type, what age were those vehicles. You had pools of vehicles, so you needed to understand how those pools were being utilized and understand the repair cycles, the repeat users, the late returns. So they were trends in the use of those vehicles from a pool. There was overall utilization reports to look at those vehicles which are being underutilized in each function, because when you're looking at a whole system efficiency, underutilization of any asset is key important. And so how many journeys a vehicle performs per day or per month was important to understand where efficiencies could be made. Did they need that amount of vehicles? Of course, we're looking at decarbonisation, so fuel usage was important, and very much fuel cost. And there we were comparing, for example, the bunkered fuel bought at a cheaper price with forecourt fuel at a more expensive price, and seeing where that was being used, and understanding the miles per gallon per vehicle, per function, per vehicle type. You needed to understand if vehicles were off-road, and how long were they off there? Was there an impact of scheduling that impacted that? And financial reports. So where were the most expensive vehicles? And these are not about purchasing the vehicles, but the cost of repairs when you compare that against the depreciation. And then you had impacts onto the system like driver behavior. drivers with harsh braking, the safety of those drivers and the incidents and accidents. Were those vehicles roadworthy? Were they overloaded? And so all of this dealt with an efficiency. And what Robert described as a focused area of decarbonisation and energy then comes into operationalised use, where many stakeholders needed to look across many reports. And to do this, we needed to pull together asset data, driver data, GPS tracking data, vehicle maintenance, fuel data, incidents and accidents and offences, and combine that mostly external data within the functions, the operational functions, human resources, finance, and operations, to deliver a complete picture of the assets utilization, idling, costs, compliance. And this broad view was used by many, many stakeholders. And what if I call out one particular example, was to look at the economic life cycle analysis. So here we're pulling out 4 vehicle types: small van, medium, large, and 4-wheel drive. And for those vehicles, they had a service, maintenance, and repair, marked there in yellow, SMR. So how much were the cost of repairs? And cost of repairs increases over time. And in the orange or red line, there's the depreciated vehicle value that is reducing over time, so that you find an optimal time for replacement. And what changed through clearer access to data was, firstly, the range analysis looked at which vehicles could be replaced. The cost analysis looked at when they could be replaced, and then budget cycles adapted. So we went from what Robert described as a planned initiative expected to deliver benefits and eliminating as much risk, to then the operational considerations of how the human driving driver behavior, the changing work patterns, and the need for both those event-based responsive emergency services versus planned vehicle use across Northern Ireland, made decisions that optimised and allowed for this efficient replacement of typically diesel-fueled vehicles with electric vehicles, by identifying those that would deliver the greatest economic benefit, and while also delivering a carbon reduction. If I move on to a second example here, in decarbonising public transport. So Northern Ireland has a climate action plan for transport that defines how transport can reduce journeys, how there can be a modal shift, getting people to use more public sector, how transport can be electrified, and how that shift can include active travel, so using cycling, wheeling, or other partially human powered transport to complement public transport. And TransLink, our customer here, have a climate positive strategy. They are leaders in the introduction of zero emissions buses. They currently have 200 zero emission buses in the fleet, and that'll rise to almost 250 by the end of the financial year. And these are primarily battery electric vehicles that use only around 40% of the energy in comparison with internal combustion engine. And when you couple that with the fact that they're using 100% renewable electricity, TransLink can then can give a clear route to net zero. So in order to deliver against that strategy, there's again a lot of stakeholders. And on the previous slide, I should have called out, there's the bus, rail, there's metro services. So there's a range of transport modes in both city and across the province of Northern Ireland. And at a big picture point of view, Safety is paramount, looking at the passenger safety, staff safety, and making sure that vehicles are safely maintained. In order to shift customers onto public transport, you need to have a good customer experience. That depends upon a service performance that's punctual and reliable. This needs to be justified by cost. So again, Robert called out the capitalization cost, and replacing incrementally bus fleet with several vehicles at a time is more feasible, for example, than electrifying a rail network where the whole network needs to be infrastructure electrified, and then there's more significant capital outlay. And you need to understand the people managing this and the assurances. So what we perform in those cases for TransLink is we help collate this data, and we look at the long-term data planning that might inform scheduling, into the short-term planning about allocating staff and timetabling to real-time dispatch. And there are a range of various reports and other tools we integrate that provide various views across this, from weekly KPIs into the annual targets. And that's kind of taking raw data from telematics, maintenance schedules, depot stats, traffic data. It's looking at planning data like the peak vehicle requirement. Do you have enough vehicles to serve your passengers? What are the timetables like? The route optimization. That goes into monitoring of the punctuality, reliability, the same way that in the mixed fleet in NI Water, what vehicles are off-road. Is there any costs associated with this and any injuries? And then looking to optimize, so predictive maintenance, ensuring the training is right, ensuring passenger loading is right, and ensuring there are the right number of spare vehicles. And when you put that together, you then get sets of reports on how, again, from a data perspective, this information is coming from lots of third-party systems, from databases, sometimes from spreadsheets, because as much as you like to try, there's still a human in the middle in cases. And we're combining that live data with historical data to provide various dashboards that are used at an operational level into an advisory level. And from the decarbonisation goals, there's a total CO2 across the whole of TransLink, broken down by Ulsterbus, Metro, Gold Line and Rail. And they want to understand by service kilometre, so for every kilometre travelled and by every passenger travelled, how that breaks down. And there's a lot of different stakeholders in there, so that climate strategy is set by an ESG committee. There is a fleet decarbonisation strategy within it. There are recorded emissions that need to be recorded and reported. And then these are tracked in various dashboards and can help show that in line with the decarbonisation plan, that the operational costs and the use of public transport is increased by making it a better service for the passengers who are shifting from using their personal car as a mode of transport. And so, to end from a lessons learned point of view, the first thing is to get as close to the raw data as possible. So that's being collected by many systems. Sometimes it gets pre-aggregated, and what you need to go is collect the raw data at source. You need to have a common data model, because different departments and subject matter experts can have a different definition of what a journey is. And then you need to understand the data life cycle. So how is information about a vehicle updated over time? What are the key events that make that fresher? You need to manage the data costs, because the more data you capture, the more you need to store. And so you can have a smart tiering system by which you aggregate and roll up and have a lifetime of expiry against relational data, and you have a smart tiering and expiry for any unstructured data you capture. But there's also the data, the cost associated with processing that data. So using efficient mechanisms, we would operate across many public clouds, including Amazon Web Services and Azure. But how you process that data efficiently, sustainably, because cloud data processing offers the opportunity to manage the sustainability of that cloud infrastructure better, but you still need to design for it. You very definitely need to understand the data needs and the user needs and talk the language of different stakeholders. From the outset, you need to build trust, because those subject matter experts are used to looking at their telematics dashboards, their transport management systems, their own view of the world. And when you start to collate that, they question seeing data in a different perspective, in a different way. And you need to build trust that that information's been captured without modification and then being analyzed. And over time, continuously, you need to monitor that data quality, recognizing that the operational context and the systems will change over time. And so there needs to be a continuous engineering approach to this. And when you put all of that together, that allows you to take the opportunity for decarbonisation transport into the operational world, to see how the models that Robert described operate in practice, to capture data that then can be checked back to validate the assumptions of those models and see if behavior has changed, and ultimately to deliver an economic reason alongside the climate reason to decarbonize transport. So I'm going to stop there and can give an opportunity now for questions.